Hello everyone, this is Lecture 15 of ComSci 141, Turing Machine Extensions. In the previous video, we introduced Turing machines and their equivalent language class, which is the recursively enumerable languages. We also talked about the Chomsky hierarchy of languages. We are now on our third topic for Turing machines, which is Turing machine extensions. In today's video, we will talk about programming tricks that we will use for us to be able to implement the Turing machine in an actual computer. We will also talk about Turing machines with restrictions and with extensions or extended capabilities, and see that even if they are more restricted or has more capabilities, they still define the same language class, which is the recursively enumerable languages. And finally, we will also talk about the closure properties of recursively enumerable and recursive languages. Okay, so let's start. So, from the previous video, we talked about how Turing machines were abstract computation models, and we said that they have an equal computing power with a general computer. So anything that a computer can do, theoretically, the Turing machine can also do that. Now, if we are to implement an actual Turing machine with our own computer, these are some of the programming tricks that we will use for us to be able to implement them. So first is multiple tracks, marking, and caching in state. So let's start with the first one, which is multiple tracks. So our Turing machine normally only has one track or one tape, right? So one infinite tape that goes either infinite to the left and right, but the thing is, it only has a single track. Okay, so you can only put one symbol at each cell. However, we can model the Turing machine to have multiple tracks. Okay, so in this one, we have multiple tracks here. We actually have 3. Okay, and we do that by, instead of writing only one symbol, we write vectors of symbols. Okay, so let's see. So to be able to simulate having multiple tracks, the tape symbols are written as tuples or vectors with k components, and that would make it appear as if you have k tracks. Okay, so for example, if you have x, y, and z, then x would be on the first track, y would be on the second track, z would be on the third track, and so on. Okay, so it makes the tape appear to have k tracks. So like here, for example, if you write O, X, and then blank, then it appears like this. So 0 is in the first track, X is in the second track, the blank is in the third track, and then for X, Y, Z, X is on the first, Y is on the second, Z is on the third, and so on. Okay, so you could make it appear as if you have multiple tracks in your single tape. So why do we want multiple tracks? Okay, so the common use of an extra track is to mark positions of certain cells. Okay, so we need to mark them. So we could leave markers on the tape so we can go back to it later. Okay, so that's the common use of having extra tracks. So usually when we do this, we have one track for data and one track for marking, and most cells on the marking track hold blanks or $signs, except for the cells that are marked. Okay, and usually we use X as the marker because it's the most convenient one. So for example, if you have 2 tracks here, the first track is the marking track and the second track is the data track, then you have A, B, and C in the data track, and A and C are unmarked because on the marking track they have a corresponding blank symbol, right? You have $signs. But B here is marked because it has an X on the marking track. Okay, so B here is marked and A and C are unmarked. So maybe later on you'd want to come back to B, so that's why you marked it, or you do that for whatever purpose it may serve you. Okay, and the next trick is to cache in state. Okay, caching in state just simply means this: you represent state names as vectors, and for example, you have Q0 as the name of your state, And what this means is you're in state Q and you're looking for a 0. So you make it appear as if the state names can hold data. And if you remember from our previous video, when we had the I think that was the third Turing machine, we had states like QCA, wherein this meant we're in the state of looking for C. Okay, look for C, and after that we need to look for A. So this will transition to state QA. And then we also had QCB, wherein the goal of this was to look for C first, and then after finding C, then you look for B. So this will transition to QB. So that is the same idea, caching in state. So you could write it Q0, meaning you are in state Q and you're looking for 0. If you're looking for 1, you might write it as Q1. Okay, so you are like packing information into the state name itself. So it seems like the state name can hold data as well. Okay, so that is what we mean by caching in state. So let's see some more examples. Let's say we have this problem. Let's say we're given a binary string as input, and our Turing machine will repeatedly copy the input string and append it to the end of the string. Okay, so the Turing machine actually does not halt or stop. So how does that look like? Okay, so it would look like this. It's a binary string, right? So you have the infinite tape. Let's divide it up. Okay, so let's say that our input string is 0, 1, 1, and then the rest are filled with blanks. So what will happen is it will repeatedly copy the input string. So it sees the 0 here. It will mark this 0, okay, so that it can come back to this part later on, and then find the first blank. So 1, 1, and then blank, and then it will deposit the 0 that it found, and then go back to find the X. So X is found here, so it will be unmarked, okay, and then go back to the next one. So it will be 1 this time, and this one will be marked as X. So find the end of the string, and this is the end of the string, and then you copy 1, and you go back again, find X, okay, unmark that, and then go to the next one, which is another 1. So you find the end of the string again and deposit it there, and so on. So you'll see that it will just repeat, because at this point, after going back here, okay, it will go to the 0, and then it will copy that here again, 1, 1, and then 0, 1, 1, and so on. Okay, so it will just repeatedly copy the input string and append it to the end of the string. So that's how it will look like. So we will have some basic states for this. P is our starting state, and it will just mark the position that we're currently in. So it will mark that cell, and remember the symbol that we saw. So it's either a 0 or a 1. Okay, and Q is the state wherein we go to the right, remembering the symbol that we saw. So it's either Q0 or Q1, and we will look for the end of the string. Okay, so we look for a blank, and if the blank is found, then we deposit the symbol. So since we're remembering the symbol that we saw here in the first part, so it was, if it was a 0, then we deposit 0. If it's a 1, then we deposit 1. Okay, and then after that, we're supposed to go back to the left and find the marked position so that we can proceed to the next symbol. So the state R will run to the left, okay, and look for the marked cell. Okay, so those are the 3 basic states. But our actual states would look like this. So it would look like SD with the vector form. So the S here would either be state P, Q, or R, the ones that we mentioned in the previous slide, and then D here is for the data. So it's either 0, 1, or a blank. Okay, so we'll use the data especially for state Q, because state Q is looking for the end, and it's either carrying a 0 or a 1. Okay, for states P and R, it doesn't really have a data that it carries, because it doesn't really need to remember 0 or 1. Okay, it's only state Q. Okay, So yeah, and then for the tape symbols, since we will have a data track and a marking track, it will look like this for the tape symbol. So it's M and then D, where M is the marking, so it's either X or a blank, and then D is the data, so it's either 0, 1, or a blank. Okay, so since it's a binary string, so it only has zeros and ones or blanks. Okay, so M is for the marking track, D is for the data track. So for example, this one is an unmarked 0 because it doesn't have a mark, it's blank. This one is an unmarked 1, okay, and these two are a marked 0 and a marked 1, meaning we can go back to this cell later on because this is a marked cell. Okay. So those are the tape symbols, and now let's see the transition function. Okay, so for this transition function, we start with state P, and we don't really have any data, so we'll just call it state P. If it sees a 0, okay, then it will transition to state Q. If it sees a 1, it will also transition to state Q, right? So it will always transition to state Q, but the difference is it will remember what it saw. So if it saw a 0, it will go to state Q0. If it saw a 1, it will go to state Q1. Okay? And then after that, since this is an unmarked 0, because the marking here is blank, right? The marking here is blank. We would change that to a marked 0 or a marked 1. So we'll change this blank into an X because this is the cell that we will come back to later on once we're done with the first part. So if it was something like 0, maybe let's change the if it was 0, 1, 1, okay, then first you're in state P, you see a 0, you transition to state Q0, okay, and then you mark this 0 so that you can come back to it later on. So when you're in Q0, you're just passing by through the ones and the zeros, you're looking for the blank, right? When you see the blank, you will deposit whatever is the data here. So it's 0, so this will be replaced with a 0. So this will be a 0 now. And then from state Q0, we'll go back to R, state R, the reverse. So you go back to the left and find the X. So since this is unmarked, this is the marked X, we found it, and then we'll go back to state P again. Okay, and then it will loop back. So this will become unmarked now. So we'll remove this marking because we're done, and then we'll continue with the next one, which is 1. Okay, so at state P, we see a 1, it will transition to state Q1. Okay, so it remembers what it saw, and then this one will be the marked 1 this time. And then again, it will look for the blank, deposit the 1 here, and then go back to state R, and then go back and find this X, unmark it, and then move to the next one. Okay, so it will just repeat. Okay, so that's how it looks like. Okay, so we're now done with the transitions for P, right? So if you're now in state Q0 or Q1, the gray ones here means that you're just passing by this symbol. So it's just a pass-by transition. So meaning from Q0, it's still Q0. The blank 0 is still blank 0. Okay, so it's still the same. You did not really change anything. You just go right. Okay, so the only thing that matters here is that you're just going to the right. So you're just passing by through them. Okay, so Q0 is still Q0, blank 1 is still blank 1, Q1 still Q1, still the same. Okay, what matters is if Q0 and Q1 sees the blank. Okay, when you see the blank, from Q0 you transition to state R. Okay, because you're reversing. And then what happens with this blank is it becomes either blank 0 or blank 1. this is still unmarked, right? But you deposit to the data track whatever it is you saw. So if you saw a 0, then it becomes 0 here. If you saw a 1, then it becomes 1 here. And you reverse the direction. It becomes left now. So it goes back to the left to find the marking. Okay? So if we're in the reverse state, we're going to the left. If we see zeros and ones, we don't really care. Okay? So this is again pass by transition only. So it's still state R, still 0. You don't change it, and you just go left. Okay? What matters is if you see either the marked 0 or the marked 1, because this is where you're supposed to come back to. Okay? When you see that, you transition back to state P. Okay? Same. State P also. So you're back here to the start state. And the marked 0 becomes an unmarked 0. Right? It becomes blank. And the marked 1 becomes an unmarked 1. And then you reverse the direction again and make it go to the right again. Okay? So you'll just repeat that until, well, it doesn't really stop. Right? So that's the transition function for our example Turing machine. So the three programming techniques that we need for Turing machines are shown here. So first is we have the multiple tracks, because of course you have the marking track and the data track. Okay, and then of course the usage of marking to mark certain cells that you want to go back into. So you have the marked 0 here and the marked 1. And then you also have the caching in state, because you have state names like Q0 and Q1, which means that you're supposed to deposit the 0 or deposit a 1 based on what you saw earlier in the previous state. Okay, so all three programming techniques or tricks are shown here in this example. Okay, so that's it. Let's now move on to the next part, which is Turing machines with restrictions. Okay, so what are Turing machines with restrictions? So we'll only actually discuss one, which is the Turing machine with a semi-infinite tape. Okay, so remember that our Turing machine normally has an infinite tape. What if it only has a semi-infinite tape? So we're kind of restricting it, or we're kind of reducing its power supposedly, but we'll see later on that even with restrictions, the Turing machine still defines the same language class, which is the recursively enumerable languages. Okay, so why is that? So let's define first what a semi-infinite tape looks like. So normally we have an infinite tape for our Turing machine, right? So it's normally you'll have a tape which goes infinite to both directions. So you have 0, 1, 2, 3, -1, -2, dot 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 dot. So it's infinite both ways. A semi-infinite tape is only infinite to the right. So it has a clear starting point here, and it's only infinite to the right. Okay, so that is what we call a semi-infinite tape. And then we'll assume that the Turing machine never moves left when it's in the leftmost cell. So if it's in this cell here, 0, and we call left on the Turing machine, so it will just stay there because it doesn't have anywhere to go to when we go left. So what we'll do is we'll actually use a 2-track Turing machine to simulate the infinite tape in both directions. Okay, so we can simulate this using just 2-track Turing machine. Okay, so how will that look like? So it will look like this. Okay, so normally we had this one, right? 0, 1, 2, 3, dot dot dot, -1, -2, -3, dot dot dot. Okay, so that's the infinite tape. For semi-infinite tape, we can just simulate it using 2 tracks. Okay, and it would look like an infinite tape still. So This one is a semi-infinite tape, but it has 2 tracks. Okay, and what we'll do is the upper track will contain the like 0, 1, 2, and 3, and then the bottom track will have the uh, the side of the negative infinity, basically. Okay, so it seems like we just folded this one, okay, into like imagine if this was bendable, you just folded it. Instead of this, it became like this. Okay, so it bended. So in this way, it looks like this is already an infinite tape, because you have an infinite to the right and the infinite to the left, but it's just on the bottom track. Okay, so yeah, so the top track will contain 0, 1, and 2. Bottom track will have the -1 and -2, and the thing that we need to notice is that the ones aligned with 0 has to be blank, so that it has the natural alignment here. And the state remembers whether Turing machine is currently on the top or bottom track, because if it's in the bottom track, we need to reverse the direction of our transition. Okay, why is that? Because if we go back here, if it was, for example, 0, 1, -1, -2, if it was in the infinite tape, if you go from 0 to 1, you're supposed to go left, right? But or from, let's just say from, not that one, maybe from -1 to -2. Okay, if you go from -1 to -2, you're supposed to go left. But in the semi-infinite tape with 2 tracks, what we'll do is we're actually going to the right. Okay, so -1 to -2 is going to the right, so we have to reverse the direction if we're at the bottom track. Okay, yeah. Okay, so that's Turing machine with restrictions. Let's now go to Turing machine with extensions. So if earlier we tried to limit the capability of the Turing machine, this time we'll try to add more capabilities to the Turing machine. So that's why it's called extension. So we'll look at 3 extensions. First is the multi-tape Turing machine, and then we have the non-deterministic Turing machine, and finally the name value store. Okay, so let's start with multi-tape Turing machine. So what is a multi-tape Turing machine? So it's a Turing machine with k tapes. So it has multiple tapes. And how is that different from a k-track Turing machine? Okay, so in the k-track Turing machine, we have this. So you only have one track, okay, or sorry, one tape. Okay, so it has one pointer, one tape head, but you divide it into like multiple tracks. Okay, so you have maybe 3 tracks here. Okay, so track 1, track 2, track 3, but you only have one tape, right? Because you have one tape head. Okay, so even if you have multiple tracks, okay, let's say this is A, B, C, then this is X, this is X, and then you have the 0, 1, 2. Even if you have multiple tracks here, you can only move this one tape head, and you can look at the 3 in unison. You can't look at A and then 1 and then X at the same time. It has to be A, 0, and X. Okay, because it only has one tape head. Now, how about the multiple tape Turing machine? For multiple tape Turing machines, you actually have multiple tapes. So you have the tape 1, tape 2, and let's say tape 3. And the thing is, they have different tape heads. Okay, so this is tape head number 1, tape head number 2, and tape head number 3. So you can move these tape heads independently of each other. Okay, so this one you think is this one is more powerful because you have the more liberty to move the tape head, whereas in this one you only have one tape head to move. Okay, so that's the difference. And the movement depends on the state and symbols under the head of each tape. So the Turing machine can actually change the state, write symbols under each head, and move each head independently. Okay, so you have more power here because you can move each head independently. However, we can actually simulate this by using just one tapes. So instead of having multiple tapes, we can do this in one tape, but we will use multiple tracks. And to do that, we will use one tape with 2k tracks. Okay, so how will we do that? So this is how we'll do it. So let me erase that one first. So instead of having 3 tracks, for example, so this is track 1, this is track 2, another tape head, and then this is track 3. Okay, instead of 3 tracks, or sorry, 3 tapes, what we'll do is we'll have one tape with how many tracks? 2k tracks. So 3 times 2 is 6 tracks. Okay, so we'll have one big tape here, but this will have 6 tracks. So let's see. So 1, 2, 3, 4, and 5. So that's track 1, track 2, track 3, track 4, track 5, and track 6. So it has 6 tracks now. And what we'll do is, well, it's quite simple. Okay, just change the color first. So let's say that these are the cells. And let's say that this has A, B, C. This one has 0, 1, 2. And then this one has maybe X, Y, Z. Something like that. So we're using one tape with 2k tracks. So we multiplied it by 2 because for each tape, one tape will use 2 tracks. Okay? One track for data, one track for marking. Okay, so imagine that this one, track 1 and track 2 is the tape number 1, track 3 and track 4 would be for tape number 2, and track 5 and track 6 would be tape number 3. So how would that look like? So it would look something like this. A, B, C, and then the marking is in here in A because that is the tape where the tape head is. For tape 2, you have 0, 1, 2, and the marking is at 2 because that's where the tape head is. And then for X, Y, Z, you have the marking at Y, sorry, because that is where the tape head is. So since we can move these marks independently, it would look like we can, even if there's only one tape head here, it's not the tape head that will move, but the markings here. So if we move from A to B, for example, so if we move from A to B, then this mark here would be removed also. Okay, and then it would be moved to B as well. Okay, so that is how we'll simulate K tapes by using only one tape, but with 2K tracks. Okay, so each tape uses 2 tracks, one for data, one for marking the head of the tape. And you can move each mark independently, so it would look like you are moving the tape head independently as well. Okay, so another example here is you have C is where the tape head is for tape 1, and then W is where the tape head is for tape 2. Okay. Okay, so that's the first one, which is multi-tape Turing machine. Next, we have the non-deterministic Turing machine. Okay, so for non-deterministic Turing machine, the Turing machine just has a choice of movements at each step. So it's not only one, but it has multiple possible transitions. And the Turing machine will accept input if any sequence of choices lead to a final state. So you're already familiar with non-determinism, right? Because we've seen this in like two computational models already. So you've seen non-deterministic finite automata and non-deterministic pushdown automata. And if you recall, if it's non-deterministic, it has this power to guess correctly which choice it should take in order for it to reach the goal that it has. Okay, so even if it has many possible choices, just trust that the non-deterministic automata or machine will find the correct sequence of choices to get to its goal of acceptance. Okay, so that's non-deterministic Turing machine. So how will we simulate this using a deterministic Turing machine? Okay, so the deterministic Turing machine will just maintain a queue of IDs, non-deterministic Turing machine IDs, or instantaneous descriptions on the tape, and you will systematically search through all IDs that the non-deterministic Turing machine can reach. Okay, by systematically searching, it's just a fancy way of saying we'll brute force it. Okay, we'll have to search through all possibilities one by one. And if you find an ID with the final state, then you accept it. Otherwise, the simulation might go on forever. Okay, so the deterministic Turing machine might never accept. Okay, but if once it finds an ID with a final state, then it's already accepted. Okay, but there's also the other possibility that the simulation could go on forever, because we don't know how many there could be a lot of possible IDs for the non-deterministic Turing machine. Okay, so it might never accept as well. Okay, so that's non-deterministic Turing machine. And finally, we have the last extension for Turing machine, which is the name value store. So this is hard to simulate for computational models because it's kind of equivalent to a computer's memory. So you have like a name value pairing. So you can think of it like a dictionary of some sort. So for example, your name value store could look like this. So you have John is assigned the value 5, Jane has the value 3, and so on. Okay, so usually you have two tapes for the name value store, and we could have multi-tapes because that is another extension, right? So we've already seen how we could simulate multiple tapes with just one tape with multiple tracks. So we can do this. So for the two tapes, the tape 1 is where you store your actual name value pairs. So you store the data here, and the format is each name value pair is separated by hashes. So you have the hash here at both ends of the name value pair. Okay, so if you see a hash, that means that it's the end of one name value pair, and then the name and the value are separated by the asterisk. Okay, so you have the name, and then once you see the asterisk, that means it's the end of the name, and then the value will follow up until the hash mark. Okay, so you'll notice here that you have star separates John and 5, and then the hash here separates John 5 and Jane 3. Okay, and then the tape 2 is the name of the value that you want to look up. So later on, if you want to find Jane, then you put it in tape 2. Okay, so that that is what you're looking for. So how will we do lookup on our name value store? So how will we get the values? So starting at the left end, compare the lookup name in tape 2 with each name in the store. Okay, if you find the match, then take what follows between the asterisk and the next hash as the value, because that is the value that is associated with the matched name. And once you reach the end of the name value store and you haven't found any, then that name does not exist in our name value store. Now how about if we insert a new value or a new entry? Okay, so we'll insert the pair nv, or replace the current value of n by v. So we could add a new name value pair, or we could update the value of the existing name. So what we'll do is, first we have to look up the name n if it exists or not, because if it exists we have to overwrite it. If it's not, then we can just add this new entry, right? So if the name n is not found, then we'll just add this name asterisk v with the hash at the end, because it's a new entry, so no problem there. But if it's found, then we have to replace it. Okay, so if we find the name with the old value, we have to replace this old value by v. Now there are three cases here. The length of the old value could be equal to the length of the new value. Okay, so what if, for example, let me erase that first. So maybe something like the name is, for example, instead of Eve, maybe you update it with name to Eve, like this. So if this is replaced with Eve, then there's no problem because it's the same length, right? But what if the new value is shorter, like name is equal to say ed. Okay, so if you just replace this with ed and you don't take care of this, it will become ede, which is wrong, right? So instead you leave blanks to fill out the extra spaces. So you leave blanks here, ed with a blank. Okay, so that you know that it's you don't leave out old symbols of the old value. Okay, so we have equal length, shorter. Now what if the new value is longer than our old value? Okay, what will happen then? If our new value is longer than the old value, so let's say, for example, the name now is updated to Adam. Okay, what will happen then? So okay, let me create a new one. Make a longer one. So name star Eve, and then maybe age 20, something like that. Okay, so what if we updated this to have name Adam? Okay, if we just placed Adam here right away, it will be wrong because it will remove this hash which denotes the end of this entry, right? So what will happen is it will become name is mapped to Adam Mage star 20. Okay, this will become the new name now because it overwrites hash, which is supposed to be the boundary for one entry to the next, right? So we can't overwrite it directly. If the new value is longer, then we use a third tape to copy everything to the right of v old. So to the right of v old is this one, right? So let's copy that to a third string, a third tape. So the third tape will contain hash age star 20 hash. Okay, so that will be the contents of the third tape, and after that, then you are free to overwrite this time. So you can now overwrite this, and this becomes Adam. And then after that, you also need to mark the position of star, which is the left of v old, so we know where to insert later. Okay, and we write v old where we write v where v old was. So after marking this, we know that we have to insert after that. So we already inserted Adam, and then copy the contents of the third tape back to the end of the first tape. So after writing Adam, we will write the contents of the third tape, which is this one, back to the first tape. So age star 20 hash. Okay, and we have now successfully updated the name to become Adam, and then it's bounded by this hash, and then age is still 20. Okay, so that is how you safely update a new name value, or an existing name value pair. Okay, so update the value. So that's it. So we saw that even with more capabilities than a standard Turing machine, so we had the multi-tape Turing machine. So instead of having just one tape, you have multiple tapes, so that's more powerful. You have non-deterministic Turing machine, so it's more powerful than a deterministic Turing machine. And you also have the name value store, okay, which has more capabilities than a standard Turing machine. But even so, they still define recursively enumerable languages. So they don't really add computing power, only convenience. Okay, so even with extensions or restrictions, Turing machines still define the same set of languages, which is recursively enumerable languages. Okay, so that's it for extensions and restrictions. Let us now go through the closure properties of recursively enumerable languages and recursive languages. Okay, so remember that closure properties are operations that if you apply the same, if you apply the operation to two languages of the same class, like for example recursive union recursive, it will always result to another to a class that's of the same class as the two operands. So recursive union recursive is equal to another recursive, or recursively enumerable concatenated with recursively enumerable is equal to recursively enumerable. Does that make sense? Okay, so I'll just write that down for example. So recursive union recursive is always recursive, or for example recursively enumerable intersection recursively enumerable is still recursively enumerable. So you remember this from our regular languages and context-free languages, right? So for the following, for recursively enumerable and recursive languages, we have the following closure properties: union, intersection, reversal, concatenation, Kleene closure, difference, and homomorphism. And let me show you in advance the properties that are closed under these languages. So for union, intersection, reversal, concatenation, and Kleene closure, they are closure properties for both recursively enumerable and recursive languages. However, for difference, only recursive languages are closed under them, and for homomorphism, only recursively enumerable. Okay, so let's see why that is one by one. So let's start with, so before that, we need to figure out how to prove that the operation that we are talking about is closed under this certain language, right? So for recursively enumerable, we will use recognizers because those are the not push down automata, but Turing machines that represent them. So you have two recognizers, M1 and M2, and their output will also be a recognizer. Okay? Whereas for recursive languages, we'll have deciders, M1 and M2, and the output will also be a decider. Okay? So deciders, remember, are guaranteed to halt, whereas recognizers are not guaranteed to halt. So this would be how the deciders and recognizers would look like. Okay, so let me so for this one, you have the decider here, wherein you have both acceptance and rejection. So this is guaranteed to stop. Okay, whereas for recognizer, it only has the acceptance pin because we don't know whether it will reject or not, because it might get stuck on an infinite loop, right? So it only has this acceptance. So later on, when we see examples of doing closure properties, for example, we have two deciders, so it will have A and R, and then A and R, and then we apply the operation to them. The result should also be a decider, which has an A and an R. Okay, so it should look like this. And then for the recognizer, you're given two recognizers, so it only has an A, it only has an A, and the result of the operation should also produce a recognizer which only has an A as well. Okay, so that's how it will look like in our proof later on. Okay, so let's see. So let's start with recursive. So for recursive, we have M1 here, which has an accept and reject. Okay, maybe a better color. Let's try to find one. Is this one better? Okay, I think green looks better, right? So M1 has accept and reject, M2 has accept and reject. So these are both deciders, right? Now, how will we create the decider for the union of the two? So we will have the acceptance and rejection, and we accept it if either M1 accepts it or M2 accepts it. So if either one of them accepts it, then it's also accepted by the union, right? Whereas the rejection will be if both M1 and M2 rejects it as well. Okay, so that's it. M1 accepts or M2 accepts, that means that the union also accepts. But if M1 rejects and M2 rejects, then it's also a rejection. So we have created a decider because it has an A and an R here. So this is also closed under recursive languages. Okay, for recursively enumerable, you have two recognizers, M1 and M2 here with the A, and the recognizer for the union would be if M1 or M2 accepts. If either one of them accepts, then we also yield the accept for the product Turing machine. Okay, so that is for union. Next, intersection. So for intersection, you have M1 and M2 here, which are deciders. And for the intersection, the decider for the intersection, you accept if M1 accepts and M2 accepts. Okay? But you reject if either M1 or M2 rejects. Right? So that's the intersection. So accept if M1 and M2 accepts. Reject if M1 or M2 rejects. So that's for intersection. Next, For recursively enumerable, you only have the decider, or sorry, not decider, but recognizer, M1 and M2, and if both of them accepts, then it's also accepted. Okay, so that is intersection. So you also have a recognizer here. So it's closed. Next, for reversal, what we'll do is we'll just reverse the input and simulate the Turing machine on the reversed input, and that would be already accepted, right? So it works for both recursive and recursively enumerable languages. So reversal of a language is also closed under recursive and recursively enumerable. Next, concatenation. Okay, for concatenation, we will use a two-tape non-deterministic Turing machine for the recursively enumerable languages. And what we'll do is we'll guess a break in the input w is equal to xy, because we might have a so we have two Turing machines, right? So this is M1, and since this is recursively enumerable, it only has accept, and then M2, which will also accept. Okay, but we're given a string like 0 1 1 2 1 1 2, something like that. We don't know how this was concatenated. It could have been 0 and 1 1 2 1 1 2, or it could have been 0 1 1 and 2 1 1 2. Well, we don't really know. Okay, so we need to break it because we need to feed one part into M1 and then the other part into M2. Okay, so the good news is, since we are non-deterministic, we can just guess it correctly. Okay, so we'll guess the break correctly. Maybe the break is something like this. Okay, and then 1 2. So we will feed 0 1 1 2 1 to M1 and then 1 2 to M2, something like that. So we'll guess a break in the input, and since it's non-deterministic, it will always guess the correct break, and we will accept it if both of them accepts. Okay, so end. So it's also accepted. Okay, so yeah, that's concatenation for recursively enumerable. So we move y to the second tape, simulate M1 on x, M2 on y, as I mentioned, and then accept if both of them accepts. Okay, so that's why we needed two tapes, because we need to break the string into two parts. The first part will be fed to the first Turing machine. The second part will be fed to the second Turing machine. So that's why we needed to move y to the second tape. Okay, so yeah. Now how about for recursive? For recursive, we can't use the non-deterministic Turing machine, right? Because it has to stop. It has to be guaranteed to halt. So we can't use the non-deterministic, since our Turing machine should be guaranteed to halt. So what we'll do instead is we'll use the deterministic Turing machine, and we'll systematically try to break w is equal to xy. And again, systematically try is just a fancy way of saying we'll have to brute force it. So let's say that you have a string a b b a b a. So we don't know how this was concatenated. So it could have been a b b a b a, or a b versus b a b a, or a b b versus a b a, or a b b a versus b a, and so on. Okay, so we'll just have to systematically try to break w is equal to xy, and M1 and M2 will eventually halt for each break. Okay, so maybe we'll try our first break, which is a b b a b a, and then feed this to M1 and feed this to M2. If that doesn't work, let's try the next break, which is a b, and for this one only b a b a, right? If that doesn't work still, then it would have to be a b b b a b a, or a b a. Okay, so accept if both M1 and M2 accepts for any break. So if any break is successful, then we will accept it. Otherwise, if we tried all of the breaks and none of them led to an acceptance, then we have to reject it. Okay, so instead of non-determinism, we used a systematic search, also known as brute force. So we had to try all possibilities of breaking. Now, it seems simple if we only have like a string of length, how many? 6. But what if we have a very long string, let's say length 1000? So we have to try 1000 different possibilities of breaking. And again, for each run of the Turing machine, it may take a long time. So 1000 times a long run of the two Turing machines might take a very long time as well. But we have no other choice because we don't have the power of non-determinism, since this one has to be guaranteed to stop. Okay, so it's guaranteed to stop, but it might take a long time. Okay, so that's the downside of determinism. Okay, so that's for concatenation. Next is Kleene closure, but it's more or less similar. The idea of Kleene closure is similar to concatenation, because Kleene closure is basically just repeated concatenation, right? So it's 0 or more copies of the same string. So for recursively enumerable, you do the same thing. You guess many breaks as possible, and then accept if the Turing machine accepts each piece. In the recursive, you systematically try always possible to break the input. So for Kleene closure, it's even more possibilities, a lot more possibilities of how do you try to like systematically break each Kleene closure. Like for example, if you have, say, A B A B A B A B, is that A B that's repeated 4 times, or is that like A B repeated twice, or is that only this whole thing repeated once? So there's a lot more possibilities here. So in recursively enumerable, you can just guess correctly because it's non-deterministic. But for recursive, since it's deterministic, you have to systematically try all possibilities. Okay, so that's the common theme. For non-deterministic, you can guess correctly. For deterministic, you have to try all possibilities or brute force it. Okay, so that's Kleene closure. And then next we have for difference. Okay, so for difference, you have the recursive. For the recursive language, since it's recursive, you have deciders. So both M1 and M2 will eventually halt or stop. And you accept it if M1 accepts and M2 does not. So how will that look like? So for M1 and M2, you have an accept and reject, since this is a decider. For M1, for M2, also accept and reject, right? So their difference, the accept and reject, how will this happen? Has to be at the bottom. Okay, so we accept if M1 accepts and M2 rejects, right? So if M1 accepts it and M2 rejects it, you have to accept that. Okay, now how about for reject? What will happen? If M1 rejects it, then it's already rejected because it's not part of M1. Or if M2 accepts it, then it's also not part of the language, since yeah, it should not be part of M2, right? But if it's accepted, then you automatically reject it. So this is the product Turing machine for recursive languages for the difference. Okay, so for recursively enumerable, however, we cannot do this because M2 may never halt. So we said that M1 should accept and M2 should reject if it's M1 minus M2, right? Because this should be okay, this one should be not okay. But if it's recursively enumerable, we only have recognizers. So for M1, we have accept. M2, we only have accept. So for this one, okay, so how will this accept? So we accept if this one accepts and M2 rejects, but there is no way for us to know if M2 is actually rejecting because M2 may never halt. So we cannot compute the difference here. So that's why this one cannot exist. Does not exist. Okay? There is no way for us to reject from M2 because M2 only accepts, right? So we cannot compute the difference. So recursively enumerable languages are not closed under difference. Okay? Because we cannot compute M2's rejection, so we cannot compute the difference. Now next is homomorphism. And for homomorphism, for recursively enumerable, we can design a non-deterministic Turing machine that takes the input W and guesses an X such that H of X is W. So we have to guess the original string that was the origin of the mapped string. Okay, how does that make sense? Okay, so let's see. Let's delete everything first. Let's say that our input string W is equal to A, B, A, B, A. Okay, A, B, A, B, A. And let's say that our homomorphism, our mapping function, is we have 3, so 0 is AB, 1 is A, 2 is B. So we're supposed to guess the X. What is the string X such that H of X is equal to W? Meaning, what was the original string of zeros and ones? So it could have been that this one possibility is this could have been a 0, this could have been another 0, and then this could have been a 1. So one possibility for X is 0, 0, 1. But that's not all. It could have also been that this A is a 1, this could have been a 2, this could have been a 0, and this could have been a 1, right? So it could have also been 1, 2, 0, 1, but there's still another possibility, like what if this was 0, this was 1, this was 2, and then this was 1. Okay, so there are many possibilities. So if you have the non-deterministic Turing machine, since it's non-deterministic, we could just guess which of these possible X's there are. Okay, and we will guess correctly because it's non-deterministic, and we will feed this to our Turing machine, and if it's accepted, then the homomorphism is also accepted. Okay, so we can do that because it's non-deterministic. Okay, it has the power of guessing correctly. However, for recursive, there's infinite possibilities for mapping. Okay, so there might be too many ways for us to map or to have the original string that was mapped into the input string. So we can't guarantee the Turing machine to stop because there's way too many possibilities for the mapping. Earlier, we were able to succeed because it was non-deterministic and we just relied on it to guess correctly. Okay, but here, since there's infinite possibilities of mapping, we can't systematically try to find the mapping. Okay, because we have to guarantee our Turing machine to stop. Since this is recursive, it has to be a decider, right? So since we can't do that, then recursive is not closed under homomorphism. So only under recursively enumerable. Okay, so that is the closure properties. And again, it's for union, intersection, reversal, concatenation, and Kleene closure. Closed siya for both recursively enumerable and recursive. But for difference, it's only closed under recursive because we can assure that M2 will stop and therefore decide M1 accepts and M2 rejects. Okay, so it's okay for recursive the difference. But for recursively enumerable, it's not closed under this because we can't guarantee M2 to stop. So there's no way to know if M2 really does reject the string. And then for homomorphism, we can just guess the mapping, the map string. So that's why we could do this for recursively enumerable. But for recursive, we can't guess it correctly. If we have to try all possibilities, there's an infinite number of mappings, so we can't do that. So it's not closed under recursive languages. Okay? So that's closure properties. And that's it for this video. So to review, we talked about the programming tricks that we can use to implement a Turing machine in an actual computer. So we had the multiple tracks, whose common use is for marking certain cells to go back into. And then we also had caching in state. So you pack data into the state name. So Q0 means that you're looking for a 0, Q1 means you're looking for a 1. Okay? And then you had Turing machine restrictions like the semi-infinite tape that you can just simulate using two tracks, wherein the upper track is the positive infinity and then the lower track is the negative infinity. Okay? So you could still have an infinite tape even with a semi-infinite setup. And then for Turing machine extensions, we discussed the multi-tape Turing machine. So you can just simulate that by using one tape with 2k tracks. So if you have 3 tapes, you can just use one tape with 6 tracks, one for marking and then one for data. Okay, we also talked about the non-deterministic Turing machine. Okay, and we can just simulate it by trying all possibilities or brute force it. And then we also talked about the name value store, okay, which models the computer's memory. Okay, and then we talked about the closure properties, so the union, intersection, difference, and so on, for recursively enumerable and recursive languages. Okay, so that's it for Turing machine extensions. In our next video, we will talk about undecidability and intractability, and this is already in the theoretical computer science topics. So this will talk about what are the limits of computation. So what can a computer do and not do? Okay, so what problems can a computer solve and what problems can a computer not solve? And if a computer can solve it, can it solve it in a reasonable amount of time, or is it only solvable in theory but in practice it takes too long to be able to wait? Like solvable in practice but it takes like 100 years to finish. So that is our next set of topics, undecidability and intractability. So that's it for this video. If you have any questions, please don't hesitate to ask me, and I will see you in the next video.